This video will cover section 4.4, the fundamental theorem of calculus. As it sounds, the fundamental theorem of calculus is very important. It connects integral calculus with differential calculus. So we've talked about the definite integral, which has the limits of integration, so the integral from a to b. So now what we're going to do is, instead of calculating the definite integral geometrically, we're going to now calculate it analytically. That is, what is the formula for evaluating a definite integral. So if we're taking the integral of f prime, then the integral of f prime is just going to be f of x. But now that we have the definite integral from a to b, we're going to need to do something with this f of x to get the actual value. So when we did this geometrically, the definite integral, we got an actual number, not just an equation. So if I were to take the integral from a to b of f prime of x, we get f of x. And how we notate this is with a here at the bottom and b at the top of this bracket. So that means I want to evaluate f of x from a to b. In other words, we're going to take f, evaluate it at our upper limit of b, and then subtract f evaluated at our lower limit of a. So what this means conceptually is, if I take the integral of, let's say, velocity, the integral of velocity would represent position. So if I want to find the integral of velocity on a certain interval from a to b, then you're looking at the change in position, where the area under the curve represents the change in position. So f would be representing the position function. So the change in position would be f at my ending time minus f at my beginning time. So that's the change in position. All right, so we're just going to get some examples here with some practice with evaluating definite integrals. So for part A, we're going to take the integral just like we did with the indefinite integral. So the integral of x squared would be x cubed with a 1/3 coefficient minus 4x. And now how we notate this, there's a couple of different ways we notate it. Some people use the brackets like it was in the definition. And so when I put brackets around that whole thing and then I say from 0 to 3, that means my problem isn't answered yet. I still have to evaluate from 3 and then it's 0. So I'm going to evaluate at 3. So 1/3 cubed, or 3 cubed, minus 4 times 3. All of that is f at b minus f at a. So if I plug in 0. Now I know that you could see that if I plug in 0, you're just going to get 0. But just for the sake of the notes, so you can see everything that's happening here, this is the process that you're going to have to take each time. So yes, all of this is just going to go away to 0, and now we can just evaluate this equation here. So 1/3 of 3 cubed would be 9 minus 12, which is -3. So this would be the area under the curve, x squared minus 4 from 0 to 3, which we would not be able to do geometrically. So now that we know how to evaluate a definite integral, that would be the exact area under that curve, so -3. Okay, now for part B. So first of all, I'm going to change this. This will make the problem a little bit easier. Let's make this from 1 to 9 instead of 1 to 8. Now, anytime we're taking an integral or a derivative, we like to simplify what we have inside that integrand. So I'm going to change this. And if you see that that's going to be the square root of 2 over the square root of x, square root of 2 is just going to be a constant multiple, so I can take that square root of 2 out in front just to make the problem look a little bit better. So I'm still going to have integral from 1 to 9, and that's going to be 1 over the square root of x, which I'm going to rewrite in its negative exponential form. So that would be x to the -1/2 dx. So I definitely don't want to take the integral when it looks like this here as it's first written. We want to rewrite it to make it much easier for us to take the integral of. Okay, so now we can evaluate. The square root of 2, again, is just going to be out front. And then I'm going to put brackets for my antiderivative. So x to the -1/2, when I add 1, will be +1/2 with a coefficient of 2. And then brackets again, this is a definite integral, so we're going to put from 1 to 9. All right, so Just the way that I like to do this, I like to keep my square root of 2 out front, and then I'm going to have evaluate my integral at, or my antiderivative at 9, so that's going to be 2 square root of 9 minus 2 square root of 1. So you can see that f of b minus f of a there. So then that will simplify down to be 2 times 3 is 6 minus 2 is 4, so that will be 4 root 2. Hopefully that's correct. I did that quickly in my head. All right, now part C, we're actually going to, I'm going to skip that and do that in class. So we're going to wait on that one. So let's go ahead and go to the next slide. I'm going to also skip part D. We'll do that one in class as well. So now let's go down to this and talk more conceptually about what's going on. So whenever we're taking the integral, let's think velocity is the graph that we're given and we're taking the integral of velocity. That means we're finding the change in position. So what if you want to find the average velocity on an interval? So we're going to notate this as v av for average velocity, or you can notate it with v with a horizontal line on top. So what this would mean is the average velocity on the interval from a to b is just simply the change in position over the change in time. In other words, if I take my change of position, in physics you use position as x. We don't use that so much in math just because we talk about x a lot more, not necessarily as position. But if x was our position function, then our change in position would be x at b minus x at a, and our change of time would be from b to a, or b minus a. Okay, so that would be the average velocity. That would be kind of like the slope of the secant line there. Now, what the fundamental theorem of calculus states is that if I take the integral from a to b of velocity, then that would mean that I'm taking the integral from a to b, if I could rewrite velocity as the derivative of the position function x prime of t. So what that's going to be is the integral of x prime is x, and then using our definite integral definition, that's going to be x of b minus x of a. All right, now what I'm doing all this for is to show that taking these two things that we just talked about, if I want to get average velocity, so let's look at let's look at this and this here, okay? And you can see that when I found the definite integral, you get x of b minus x of a, which is in the numerator here. So let me rewrite this equation. What I'm going to do is I'm going to multiply both sides by b minus a. So that means I'm going to get average velocity, so v average, and then I'm going to multiply by the denominator b minus a. Okay, so what would that equal? That would equal the numerator that I have, x of b minus x of a, which is equal to the integral from a to b of velocity. Okay, we're stating all this to show you a new equation, which is called the average value of a function. So if I want to find the average value of a function, you can see kind of how we did this. We have this 1 over b minus a. So if x of b minus x of a is the integral from a to b, and then I divide by b minus a, that gives me the average velocity. So if I want an average value of a function, then the definition of that would be the average velocity of a function is 1 over b minus a. And then how do I get that change in position? Well, you get that from the integral. So that would be the integral from a to b of f of x dx. So if all this theory was a little bit confusing for you, just remember that if you're finding an average value of a function, so average value of rate of change or whatever function you're looking at, this is the average value formula, which you need to memorize. So this is called the average value formula. All right, so let me just show you graphically what this is representing. Sometimes it helps to see it graphically. So if this is the graph of f here, all right, so these are both the graph of f. If I were to find the integral of f from a to b, then that represents the area underneath this curve. Okay, so if I were to calculate the area underneath this curve, that represents that integral from a to b. Now what the average value states is the average value of f What that means is sum f of x. So let's say that average value is here. So f of x is a y value. So let's say that this average value of f, it's a y value somewhere on my curve. So if I draw this line across, and I say that this is the average value, okay, then if I create the area under that line, so that means I'm just going to have a rectangle. Okay, if I were to calculate that that was the average value of f, then the area under this rectangle is equal to the area under the graph of f. That's what that means. So in other words, you could think the average height is equal to 1 over b minus a times the integral from a to b of f of x dx. Where that becomes important is if I'm looking for an average velocity, I'm giving velocity, then you would find the total change in position and then divide by the change in time so that you could find the average velocity over the given interval. So again, this is a little bit confusing, but as we work more problems, hopefully it'll become a little bit better for you. Okay, so now we're going to do an actual example for finding the average value of f on the interval from 0 to pi. So this is where you would need to have memorized your formula. So remember, the average value is 1 over b minus a. And so if they give me an interval, 0 would be a here, pi would be b. So our integral would be, or our average value would be 1 over pi minus 0 times the integral from 0 to pi of our function, which is sine x. Okay, so we're going to evaluate this definite integral, and the only thing different just to find the average value is you multiply by 1 over pi minus 0, or you divide by the change in time. All right, so this would be 1 over pi. The integral of sine is negative cosine, and I want to evaluate that from 0 to pi. So this is going to be negative cosine of pi minus negative cosine, which would become positive cosine at 0. And then if you calculated all of that, cosine of pi is negative 1 times a negative is a positive. So this is 1 over pi times positive 1 plus cosine of 0 is also positive 1. So 2 times 1 over pi is 2 over pi. So that would be the average value for sine on the interval from 0 to pi. In other words, what that means is if you found the area under the curve of sine from 0 to pi, and you found that area, and then you also went to 2 over pi, that y value, and evaluated the rectangle area from 0 to pi, they would have the same area underneath. Okay? That's what that means. All right, we're going to actually skip the next problem as well. You do not need to know the mean value theorem for integrals because actually we just talked about that. So it's just that same height at which the area is the same as the area under the curve. Okay, so we're not going to do that problem. So we're going to talk about one last thing. So some functions are defined as definite integrals. That is that they can only be defined as definite integrals. It gets a little confusing. And actually, now that I'm thinking about it, I think this will be better if we do this in class. So I'm going to stop here, and whatever we didn't do on here, we'll do in class. And we'll talk about these functions being defined as definite integrals, because I'd like to approach this in a little bit different way. All right, so I hope the fundamental theorem of calculus made sense, and we'll talk more about this in class.